All right, today we're talking about section 8.2, algebraic vectors. Yesterday, or in the previous recording, we talked about how we know that vectors have magnitude and direction. Magnitude is the force that they have, direction is the direction that they're going in. Yesterday we talked about that visual, the geometric. We really talked about direction as degrees, and the magnitude was a distance or a length of something. And today we're still going to have the magnitude is going to be seen as the distance, but instead of saying in degrees, we're going to use the Cartesian coordinate system here. So if we have a vector that starts at 0, 0, and it goes to 3, 5, this vector here, sorry about that, it starts at 0, 0, and it goes to 3, 5. The direction is, and we're going to just say, oh, the direction of that vector is 3, 5. That's my direction. Magnitude. Well, magnitude is the distance. Well, the distance isn't bad. It goes over 3 and up 5. So it has 3 here, 5 here. My distance is going to be 3 squared plus 5 squared, 9 plus 25, or 34. And since it's a Pythagorean theorem, my distance is going to be the square root of 34. So that would be my distance here for this particular problem. Okay? So I'm going to kind of get rid of that for now because I'm going to actually need that space here. I'm actually literally like taking it out of here for now. All right, I'm going to need that space. Now we're going to go to our second one. What happens when we have this distance here and it goes from negative 8, 2 to negative 2, 7? Well, it was really slick when this one was at 0, 0. So what happens if I just literally moved it so it's instead of starting here at negative 8, 2, I made it so it starts at 0, 0. Well, then I'm over 1, 2, 3, 4, 5, 6, and I'm up 1, 2, 3, 4, 5. So I have a 6, 5. I'm at the point 6, 5. That's the direction that that vector is going in. And direction here is a lot like the slope, okay? Then to find the distance covered, I really just need to take the square root of 6 squared, plus 5 squared. 36 plus 25, 60, or 56, wait a minute, I got to write it out. 36 plus 25. 50, 61, square root of 61, I think I'm right there, is what we were dealing with here. And so that would be my magnitude here is the square root of 61. This would be my distance. So what we're doing is it doesn't matter. You can kind of move everything around, but it really helps to always be thinking of, okay, where would it be when in concerning to 0? So even if we have one and instead of starting or it goes in a different direction, I can use my Cartesian coordinate system and say, oh, it ends here. So even if it ends down here, you can always say where does it end. And so that's a lot what we're going to be doing today is talking about where does something start and end. All right, so we're also going to be dealing with 3 dimensions here in a minute to begin with. But let's talk about what if I don't always want to write down my Cartesian coordinate system? What if I want to do it in just using algebra? Well, that's really actually pretty easy. The process is, what we're going to do for this direction is we take and we're going to just say, okay, we need to figure out what's the change in x's and what's the change in y's. It's a lot like what we did when we found the slope. Except here what we're doing is we're going to find the change in my x's here by taking the second x minus the first x. The change in my y's by taking the second y minus the first y. So my answer here would be negative 8 and positive 8. All right? Then if I'm finding the distance, it's really just the distance formula that we've dealt with before, but it also happens to be just that x value that we found plus the y value that we found and square it. So this would be the same thing as a square of 128, which is really 8 times square root of 2. You can usually, it depends on the problem, the word problem, if it's okay to put that into a decimal or if we want you to leave it in that radical form. So even when there's 3 dimensions, we're talking about our third dimension, our x, y, and our z, the process is really pretty similar. We're going to find the differences in my y's, the differences in my x's, and the differences in my z's. The only thing that's changed here now we have that addition of the z. And so here this would be 5, this would be a 0, and this would be negative 2 here. All right, so that is my direction for my vector CD. That's my direction. Now we have the magnitude. What's the length here? This is where we just find that square root of what we found our x direction to be plus our y direction plus absolute value of our z direction. Okay, so here it would be 25 plus 0 plus 4 square root of 29. All right, so now, just a reminder, when we're talking about this vector now, you're going to see a lot of things like this, like for the vector. What this means is this is showing a vector, which is kind of like a line. It has a start and an end, all right? And that this is the start is always at 0, 0. And that the end is going to be at that point that they tell us. So it really is telling us the direction, all right? So it's telling us the direction, and it represents a vector. All right, so it kind of represents the vector and the direction at the same time because it tells us the direction in relation to a 0, 0. This is just telling us a point. It's telling me where a point is on my Cartesian coordinate system. It's not telling me from 0 to that point or anything like that. It's just telling me the coordinates of a single point when there's parentheses and versus that straight line or kind of the Pac-Man symbols. So now, here, when we have vector addition here, and we'd have to have our vector symbols here. Sorry, guys. My vector symbols went away. All right, so we have this vector addition and subtraction and scalar multiplication here. So D plus C, when we're having the D plus C, like how do we add two vectors together? And we kind of showed how you added them together and what happens when you add them together. When we had the parallel value and the like we did this, and we had two vectors, and there'd be two vectors, and then the one comes between it by doing that. That's really what we're doing here, but we can do this algebraically. We don't have to draw it out and kind of try to figure it out each time this way. Let's do this algebraically. So the D, what we do, it's a lot like what we do with matrices, is we just add the X values and add the Y values separate to each other. So since we're adding here, we're adding here. So this would be a 1 and a 10 here. That's my new matrix, all right? Same thing here. With subtraction, we're just subtracting our X and our Y value, or here's our X values being subtracted. Here's our Y values being subtracted. So this one here would be 9, 8, and that would be our value. With scalar multiplication, we're just multiplying our X values of our C by a 3 and the Y value of C by a 3. So my answer here would be negative 12, 3. Okay. So now, same thing when it's a triple. Don't let the fact that you have a triple throw you off anymore. It's the same process. So D plus C, all we're going to do here is we're going to add the X's together. We're going to add our Y's together. Whoops. And we're going to add our Z's together. 6 and a negative 4 is 2. 4 and 3 is 7. Negative 1 and 2 is 1. That is our answer vector for what is a vector when that's the sum of two other vectors. Okay? So in other words, again, if this one, for each one of those, if that started at 0, this is going to be the direction of the vector that goes in between them. For this one, C minus 3D, first I think it would be helpful to, I'm going to write down C here, and to calculate what is 3D. So 3 times the 6 would be 18, 3 times the 4 is 12, 3 times the negative 1 is negative 3. Then we can go ahead and subtract. Negative 4 minus 18, 3 minus 12, and 2 minus a negative 3. So my answer here, negative 4 minus 18, negative 22. 3 minus 12, negative 9, and then this would turn out to be a positive 5. That is my answer vector right there, a resultant vector that we deal with. All right, so unit vectors. Unit vectors are kind of a little different. So what they are is they're a magnitude of 1 unit. When we are dealing with the X value, we're dealing with each unit is an I. In the Y-axis, each unit is a J, and then when you're talking about the Z-axis, it's a K. At this point, I have to pull one of those because I said so. Later on, it kind of maybe makes sense, the Y, and it's kind of like someone just got to decide that at some point, when the X is 1, it's 1 unit. When the Y is 1, or it's an I, and the Y is a J, and the Z is a K. All right, but let's talk about this. Let's say we have this point. Sorry, guys. This point out here, and it's the point 3, 4. All right, to get to that point, we have to go 3 single units to the right and 4 single units up. 1, 2, 3, 4. All right, so what we have is like 4 of these little J's that are sitting there going right on top of each other. These I's right here. So what this is, if we said what's the unit, we'd actually say 3 of the I's plus 4 of the J's. Okay? And really what I need you to be able to do is to take a vector like 3, 4 and change it into 3i plus 4j. So let me give you an example. So here, excuse me, so when we have this, we're trying to find the sum. So first we need to find EF. All right, so finding EF is really, again, we've done this before, it's about finding, it's about finding the distance or finding here what is the difference between the x's. So I'm going to go 2 minus a negative 4. Then I'll do the y's, 5 minus 3, and the z's, 7 minus 6. So this answer here would be 6, 2, 1. That's the direction of the vector EF. So the vector EF can now be shown with 6, 2, 1. Now I need to do the second part, which is show this as a sum of unit vectors. Well, don't make it harder than it is. It actually is pretty basic in that it's just 6 i's, 6 of the x values, plus 2 j's, 2 of the j values, plus 1 k. All right, and 1 of the z values. And that's really just how we show it. So that is, in the end, our final answer. It's a way to show a vector as the sum of some properties. And the hard thing at this point is understanding, well, why do you want me to do that? And that's really helpful for some looking at some things in some physics ways. I know it's hard to see it now. Let me do another example fairly quickly here. So again, my first step is I was asked to find this vector EF. I have 2 ordered triples here, and I need to see what's the vector that would be between them. And so what I have to do is I have to take the second x minus the first x, the second y minus the first y, and the second z minus the first z. Okay? And so, I'm trying to rush here, I'm sorry. This would be 1, 8, 15. Now, same problem, I need to put it as a unit vector. All right, as a sum of unit vectors, all right, or the sum of units, you would have 1i plus 8 j's plus 15 k's. And that's our answer there. All right, so 1 of the i's, 8 of the j's, and 15 of the k's would get you to that right vector that we're working at. What I want you to kind of work on here, and the assignment for my traditional classes is 12 through 30 on page 502. There's page 502, and then this is like the second part of it. If you're in the hybrid class, I just want you to continue working on the packet. Maybe look at a few of these examples in this section to make sure you're on track.